Hello there, calculus fans. I just started a new quarter teaching calculus, and I had this idea yesterday of what's a sort of a practical, physical, visual example I could use to start from just to illustrate the idea of functions and their derivatives. And so I thought it would be funny if I went around campus and I measured the height of a few things. It was a little embarrassing, but I recorded myself throwing a tennis ball trying to get to the top of George Washington's head. I went over to this thing that looks like a bowling pin or a peanut. I threw to the top of that. And then I went over to the columns and I threw to the top of that. And I'll talk a little bit about each one. The interesting rule I discovered, and I'll talk about this. I'll probably make a separate video that goes a little bit heavier into the math. But basically I found that if you take the time, and I'll talk about how I solved this, but it required just a little bit of calculus knowledge. This is the time it took, and I took a video of it, and I'll show you that in a second. This is the time it took in seconds for it to go all the way up from my hand and all the way back down to my hand. And that was 2.83 seconds. What I found was an example where actually the using feet was better than meters, because if you double that and square it, it will tell you that distance. And I'll explain how I got to that. So I'm calling this the Dr. Loveless double it and square it method. So if you have a stopwatch and a ball, you can measure the height of something. You throw it to what it looks like about, this is just a rough estimate, but you throw it to what it looks like about the highest point, you let it come down, and you time it. If it takes 1 second to go up and come back down, it turns out to be 4 feet. If it takes 2 seconds to go up and come down, you double it, so that would be you double it, which would be 4, and you square it, which would be 16 feet. So it's kind of interesting. I never really thought about that before. That's assuming there's not much air resistance. I'm just using a tennis ball here. I realized that this was really the limit of what I could throw underhand easily. It turns out you could throw it overhand and throw it over the top, which might have been a better experiment. Even if you throw it at a little bit of an angle, the height still would be appropriate and the time would still be right. So that's kind of fun. Next time I do this, I'll bring a tennis racket so I can hit it much higher. The only thing about this is a measurement from where I throw and catch it. So I need to add my height to it. And from where this one I threw from about 7 feet. You'll see in the video that I released it from about 7 to 8 feet high. And so in total, from the ground to up there, it's going to be about 38 to 40 feet. So somewhere in the range of 38 to 40 feet. Adding 5 feet if my hand was 5 feet above the ground to start. But I did have to kind of jump and throw that. I did that one a few times. The height of the peanut is going to be about 5 to 6 feet more than this. So I don't know, 22 feet-ish. And the height of these is going to be about, I threw it from about 5 feet. So I'm not being super precise here. 28 feet, let's say. But I want to show you this as an opportunity here's an example of something you can physically see. I'm going to give the formula for height with respect to time. And I'm going to give you the formula for the velocity. And ultimately, when we're doing calculus, we talk about how this is positive velocity and this is negative velocity. And I think this is a good place to start in a calculus course to get a feel for what's going on. And then I'll end with a little discussion on this. And I'm just going to show the video now, but I'll end with the discussion about each of these landmarks. And then in a separate video, I'll get into the math a little more. But anyways, here's what I did. And here's real time. And it goes so fast that I'm probably going to do it half time. But there I was throwing. I did it several times. I ran into some students I knew. I didn't quite get it all the way to the top. I got pretty close. And you can see I really had to heft it. And unfortunately, I'm looking like I've gained more weight than I want to admit. But anyways, let's get back to this. Here's then what I did. So I'm going to slow this down to about half time. And then I made a Desmos using these formulas, well-known formulas. A physics teacher could do this, anybody could set this up. But I'm going to try to set it in motion the moment I let go. I think I was a moment late there. But you can see I'm pretty close. Boom. That's it. Now I'm going to show you it where this axis is the time. And I'm going to draw a little parabola for that. So the reason it's going to the side is this is the time, the number of seconds. Maybe I'll label it so you can see what the height is. All right, let's try to do it again. Here it comes back down. Go. So we're going up. There's the tennis ball. It comes back down. So at about I did it this with I opened a separate editor so I could get it to the millisecond, but it was 2.83 seconds. I know it's a very unusual way to measure the height of that, but it was 2.83 seconds to get to the top. And so then the natural question might be, okay, halfway between there was its highest point, that 32, top of that parabola. Now, a lot of that you can do without calculus, but I'm using this as a starting place for calculus. So let's look at that again and maybe shrink it a little bit. What I meant to do is this. Sorry, just a moment. And what I would like to do is pull up this other window. And this thing is what we call the velocity of that thing. So same thing, I can slow it down a little bit. All right, let's let it go. This is the velocity. I should have started at the same place of that thing. So we say ready, set, go. It has a positive velocity of about 20. It starts at about 40 miles per second. And when it's at the top, the velocity is 0. And when it's at the end, the velocity is negative 45, which was the velocity at the start. That's what this is. So I'm going to pause this somewhere in the middle, right when it's about at the top. That's the velocity. Notice it looks very different than the height graph. And that bothers students when they're first doing calculus. And big part of what we're doing in calculus is connecting those two graphs. Okay? And so I hope that this gives a starting place for all my calculus courses. Let's get rid of the ball and just look at the time. You know, when you're at the peak, right there, is the same place when this is 0. Velocity is 0 there. In fact, the theme in calculus is whenever you want to know where the high point is or a low point, you find the slope of the tangent formula or the derivative and you set it equal to 0. Before you get there, you're on your way up. Positive slope. So that means the ball was on its way up. And that bothers people a little bit that this is on its way up and this is on its way down. But you have to remember that this is slope or velocity, positive velocity. So if we set these things side by side and let it go, I'm going to have to time it. Let's have it repeat. Go, and I'll start this one when it gets one cycle through. Right now. So there they go. It's at the peak when this is 0, and then it's negative here. That's it. That's what we're going to be studying this term. The truth is you can find the derivative formula, the formula for this line, very quickly for almost any function. And calculus gives you the way to do that. This is just a simple example of it. So the connection between those two graphs is really one of the fundamental ideas in calculus. The fact that we go from, we'll make various comments like if the slope goes from positive to negative, then that means this graph switches from uphill to downhill. And that means this is a maximum. There's a funny name for that called the first derivative test because the first derivative tells you that. So there's that one. And I did a few more of these just to show you how badly I embarrassed myself. So here's the peanut. When I was doing this, a student walked by and talked to me, and several people looked at me funny. I didn't actually, let's see, I worked this out. So let's do the peanut. The peanut I said was 1.96 seconds. So I'm going to change this to 1.96. And when I post this video, I'll share these animations with you in case you want to play around with them. So here we go. Ready, go. Oops. Ready. Let me see the timing here. Good. Ready, go. At the top. Oh, I did it a little late. That was way too late. Here it comes. Boom. Ooh, that time looks slightly off. Looks a little too long. Anyway, there's the peanut. And then let's go back and look at the columns. Looks like I overthrew that one a little bit. 2.43 seconds. Let's put that in here. 2.43 seconds. And here we go. Boom. That's much shorter than that. Oh, it's because maybe I'm not filming it right from when I release it. Oh, my timing is off here. That's the problem. I can tell you that I slowed it down and actually measured it, but I realized the syncing of timing is a little off because this is not true time on Desmos. It's just whatever I set it to be. So I need to speed up the time, but it only gives me increments, so I can't quite make it the same unless I get lucky. Okay, so there you go. That's the goofiness I did today. I did those 3 spots. I'll end with a little discussion. In a separate video, I'll talk about the math of how I figured out it was twice that time squared. The George Washington Monument's been there for a long time. It said dedicated in 1909, but in 1938 they added a pedestal. I couldn't find a distance measurement, except I did find there was a article about when it was defaced many years ago, and they said it was 38 feet tall. I assume that means including the pedestal. It was pretty close. The peanut is an artwork that was put up in 1996. It says that people call it the peanut or the bowling pin, but it weighs 8,000 pounds. It's 23 feet tall. Pretty close. The Sylvan Grove, which is where these are, you should see if you can try to find these on campus. A Sylvan Grove means, I had to look that up, I thought maybe it was named after somebody, but it just means a amphitheater place like that. So that's not named after a person. These have a really long history. The original building, a lot of these names will be familiar to UW students, but Danny and Bagley, I'm teaching in Bagley Hall this term, made that first, there were 2 pioneers that made that first building of the University of Washington. It had these 4 pillars. And then later they were moved and put in this spot. And then a few other famous names, Professor Meany, and there was one other one, Condon. I don't know why Condon had to get the building so far away. Sorry, Professor Condon. But Meany and Condon named the 4 loyalty, industry, faith, efficiency, or life. And then they were moved to that grove. And supposedly there's some sort of tradition of touching the one that you're most associated with. Now, when I tell people when I come to the UW campus, I always take, if it's family, I take them into this grove where these giant pillars are. And I say, this is the most relaxing place on campus. It's a very calm place. I'm sorry, I had to give that. It's the calmest place on campus. All right, so there you go. There's a little bit about an example where you have the height of an object. That's actually a parabola. It's a pretty accurate model. And the velocity of that is what we call the derivative. So I hope that gives you a physical starting place as you're trying to grapple with the idea of functions and their derivatives. You can think about this tennis ball being thrown and height and velocity. All right, I hope that gives you something kind of interesting, or if anything, made fun of me a little bit.